Okay then guys, I thought I'd run you through the little bit of bookwork for this section on homogeneous second order linear differential equations with constant coefficients. Here they are here, a, b and c are constants of course. Y double dash just means the second derivative, which is d2y by dx squared. Y dashed is the shorthand notation for dy dx, and you've got y. So you've got a y double dash plus by plus c, y equals 0. A, b and c are constants. The method here then, when solving these, is to first form the associated auxiliary equation. That's what it's called. So we formed that. So once these are in the correct positions, we can read off the correspondences. So this is A, B and C. So you've got a quadratic here in lambda. We just write that A lambda squared plus B lambda plus C. This is called the associated auxiliary equation. And then we solve the quadratic equation here to get roots. And there's three possible cases that can arise. When you have real distinct roots, we write this solution. When you have repeated roots, then we have this solution. And then when we have complex roots, when b squared squared is less than 4ac, then we have complex roots. And then we write down, so the complex roots are lambda 1, lambda 2. And we can write them as complex numbers, alpha plus beta i, and alpha minus beta I, and in that case we write a sine plus b cos beta x brackets e to the alpha x, and we can just read off the numbers there. So that's the bookwork then, and we'll refer back to that on a regular basis, but I'll just show you a very simple example then in this intro here. So the first thing we do is there's one lot here, so let's write down the associated auxiliary equation then, shall we? So we get 0. Now we can factorize that. So we can do lambda, 2 1s, isn't it? Plus 1 plus 2 equals 0. And that tells us then that lambda plus 1 equals 0, or lambda plus 2 equals 0. And that gives then, move the 1 over, lambda equals minus 1. And the second one gives lambda equals minus 2. So we can see what case they are, can't we? They're both real numbers, they're real distinct. So if we go back to our bookwork, which we'll refer to as I say, we can see that real distinct, that's case 1, and we can write down the answer here. So let's go back then to our problem, and so we can say case 1 then gives, and then we write down the answer. So y is equal to a e to the first root, so say minus 1 then, plus b e to the second root, which was minus 2x, wasn't it? There's a 1 there. And don't forget there was a 1 there when we were doing the associated quadratic, because there's always a 1 lot of something by default. So there's our general solution then to this second order equation. That's the general solution. If we have initial conditions, which we've got here sometimes, and we do in this section from question 12 onwards, then we can invoke the initial conditions. But you'll notice there's a y naught is 1 and y dashed. Well, the first one just is shorthand for when x is 0, y has the value 1. So you could put that in here straight away. So let's do that then here, just by way of example. So y naught equals 1, that gives when x is 0, y is 1. So put 1 in there. X is 0, e to the 0 is 1, so that would be a. And then e to the 0 would be 1, so plus b. And that would be a plus b equals 1. That would be one equation that we have in A and B. So when we differentiate, as you can probably see now, let's differentiate then. So differentiating gives so let's quickly just differentiate it. Differentiate the way you get y dash. Differentiate the function. This is a function of a function, so the minus comes down to be with the a lots of e to the minus x, and similarly the minus 2 comes down to be with b, minus 2b, e to the minus 2x. Now we can invoke the initial condition, so y dash naught was equal to what we said at the outset, if you see there, 1. So nice easy initial condition in this example gives. And then what we can do is we put in the values, so y dashed is 1 when x is 0, so e to 0 is 1, so that's minus a. And this would be e to the 0 would be 1, so that's minus 2b. So you can see there, when you can start moving things around, of course, but we've got two simultaneous equations in A and B. And so then we then solve these for A and B. and this gives rise to the particular solution. So this leads to what we term to the particular solution. So there we are. That's the process which we're going through solution in this section. So all the best with it, and I'll catch you in the next section. Cheers!